In this video, we're going to focus on rate of reaction. Rate is usually expressed as change in some quantity divided by time taken for the change. Whenever we talk about speed in physics, we write speed as distance covered divided by time taken. Or we can write change in location divided by time taken. But as we are talking about chemical reactions, for a chemical reaction, as the reaction proceeds, the concentration of reactants decreases and the concentration of products increases. So for a chemical reaction, we can write rate is equal to change in concentration divided by time taken. If the rate is measured for a long interval of time, then the rate is called average rate. So the average rate will be final concentration minus initial concentration divided by final time minus initial time is equal to del C upon del T. But if we measure the rate for a very small interval of time, then the rate is called instantaneous rate. So our instantaneous rate will be limit the time interval tends to 0, del C upon del T is equal to dC upon dt. Unit of rate. As the rate is written as change in concentration divided by time taken, we express concentration as mole per liter divided by time. So the unit will be mole per liter per time. We can express time as second, minute, hour, day, and year. So the unit of rate can be mole per liter per second. It can be mole per liter per minute. It can be mole per liter per hour. It can be mole per liter per day, and it can be mole per liter per year. Let's take a hypothetical reaction A to B. Here A is our reactant and B is our product. We can express the rate of this chemical reaction in terms of A or in terms of B. As the concentration of A decreases as the reaction proceeds, so we can write rate in terms of A is equal to negative sign change in concentration of A divided by change in time. The significance of this negative sign is the concentration of reactants decreases as the reaction proceeds. We can express the rate in terms of B. So the rate will be positive sign of change in concentration of B divided by change in time. Here, the significance of positive sign means the concentration of B increases as the reaction proceeds. So the change in concentration can be positive or negative, but the rate of a chemical reaction is always a positive quantity. We have to remember this. Then we are going to draw some graph for rate of reactions. We take concentration in y-axis and time in x-axis. So our graph will be like this, because as the reaction proceeds, the concentration of reactants decreases. If we take 2 points on this curve, here and here, the initial concentration is here and the final concentration is here. And the initial time is here and the final time is here. So the change in concentration is del C, and the change in time will be del T. So the average rate will be del C upon del T. If we add these 2 points, for example, this point is A and this point is B. If these 2 points are added, we gain a straight line, and the slope of this straight line, which is tan theta, is the average rate of this chemical reaction. But if we want to find out the instantaneous rate of a chemical reaction, we again plot the curve. In x-axis, we take time. In y-axis, we take concentration of reactants. So as the reaction proceeds, the concentration of reactants decreases. If you want to find out the instantaneous rates at this point, we just draw a tangent at this point, and the slope of this tangent will give us the instantaneous rate. So we can write rate is equal to negative sine of change in concentration of reactants divided by change in time. If we want to express the rates in terms of products, we take the concentration of products at y-axis and take the time in x-axis. As the reaction proceeds, the concentration of products increases. If we want to find the rate of reaction at this point, so we just draw a tangent at this point, and the slope of this tangent gives us the instantaneous rate of the chemical reaction at this point. So we can write rate is equal to positive sine change in concentration of products divided by change in time. Let's take a reaction, the decomposition of hydrogen peroxide. It gives us water and oxygen. So we have to balance this chemical reaction. So here we give 2, here we give 2. So the reaction is balanced now. As you can see from this reaction, when 2 moles of hydrogen peroxide consume 2 moles of water is produced and 1 mole oxygen is produced. So we can write the rate of disappearance of hydrogen peroxide is equal to rate of appearance of water. As you can see, when 2 moles of hydrogen peroxide consumed, 1 mole of oxygen is produced. So we can write the rate of appearance of oxygen is the half of rate of disappearance of hydrogen peroxide. Here we can write positive sign 1 by 2 d of H2O divided by dt. So we can write the rate of this chemical reaction is equal to negative sign 1 by 2 d of H2O2 divided by dt is equal to positive 1 by 2 d of H2O by dt is equal to positive dO2 by dt. So let's take a hypothetical reaction. Ka plus small b capital B gives you small m capital M plus small n capital N. So we can write the rate of this reaction is equal to negative sign 1 by A, change in concentration of A divided by change in time is equal to negative sign 1 by B, change in concentration of B divided by change in time is equal to positive 1 by small n, change in concentration of M divided by change in time, positive 1 by small n, change in concentration of N divided by change in time. That means rate is equal to 1 by A into rate of disappearance of reactant A is equal to 1 by B dot rate of disappearance of reactant B is equal to 1 by small n dot rate of appearance of product capital M, 1 by small n dot rate of appearance of product capital M. So this is our rate expression for any chemical reaction. So this is our lecture about rate of reaction. In the next video, we are going to solve some problems regarding the rate of chemical reactions. So thanks for watching this video and don't forget to like, comment and subscribe.